Hello there, welcome to the Learning of Engineering tutorials. In this video lecture, we are trying to see what are the principal stresses are acting on a particular plane. As we know, so there we can see a member is going to be subjected to a like direct stresses. Like direct stresses are acting which are two mutual perpendicular directions, right? The same I have illustrated with the figure. So that's going to be A, B, C, D is going to be the one of the plane in the two-dimensional. It has a third dimension also there. The thickness we are considering the unit. And this member is going to be subjected to the sigma x in the x direction and sigma y is in the y directions. So now can you see the BC plane is perpendicular to your applied stresses. And similarly AB and the DC is going to be perpendicular to the applied stresses in the y direction. So there we can see. Because why we need to do the principal stresses? When we are going to be talking about the direct stresses, only the member is subjected to the tensile forces or the compressive forces. The governing equation stress is equal to load by area, that's more than enough. But when the member is going to be subjected to more than one force or one stresses, so then what will happen? We need to find out the resultant component of that. So then what happens for this? To identification or to find out the magnitude of the resultant component, we are developing the equation by using the principal stresses. In the same we have seen in the previous video lecture also. So now we can see the same that we are going to be representing in the three-dimensional object. So can you see here? This is going to be the three-dimensional object where these stresses are going to be acting in this face or on this face. So these faces are going to be suffering. So now what I am going to do, I want to find out the loads are acting on the face BC and it has a unit thickness. So that I am going to be taking the Px is going to be on the face of the either BC or AD, that's going to be equal like forces we have taken. So that's the Px is equal to, what is the formula we do have? So that's going to be the stresses acting on that member into the area we need to be considered of the BC. So now can you tell me what is the area of the BC? That's going to be height into this thickness we need to be take it, right? So that I am going to be taking sigma x into BC into 1. Then finally simplification sigma x BC I have written. That's Px is equal to. So right, that's going to be Px is equal to, that's going to be sigma x BC. And similarly there is another force also going to be acting on this the surface, that's going to be CD is going to be normally to the applied force of that one, that I am writing Py is equal to. So what is the Py here? How to write it? That's going to be the shear stress into that I am going to be taking here, that is going to be your FB face or AB face we are going to be taking, right, into the unit thickness we are going to be considering, right? But if I am going to be taking the oblique plane over here, so then the final equations, that's writing Py is equal to sigma y into AB I can take it, or CD also we can take it. Now it is very clear these faces are normally to the applied forces. But now I am going to be considering one, the plane is going to be inclined to the surface. So then what happened? That I am going to be considering here. And this point I am going to be say the F and it is making an angle theta. Now our prime concern is that we need to find out the stresses on your FC and with the inclination of this theta. Then how we are going to be modifying these equations? As we know, when the line is going to be passing like this, so that I am going to be draw illustratively over here. So now we can see here, this is going to be your BC face, right? So then this is going to be your face AB that I am going to be taking over here, that is the inclined plane. So this is going to be your F and making an angle theta. And here that's going to be the Px is acting and here the Py is going to be acting. So now I want to simplify here, that's going to be Px is equal to sigma x into BC, that's going to be the right. But here we are going to be taking only the face of the FB. So that the Py I am going to be writing in terms of the Py is equal to sigma y into FB I am going to be writing over here. So now can you see these forces are going to be passing like this. So can you see these, the Py as well as the Px loads are inclined to the your face of the FC because this is existed in the oblique section. So now I want to resolve the Px. One is going to be normal to this one is going to be tangential tangential to this one in the x direction. Suppose if I am going to be taking the px force, so this I am going to be taking over here, this is going to be your px, right? This is going to be acting in this direction. So then what will happen, I am going to be taking here is the normal, this is going to be the pnx I am going to be considering, because that normal force is generating, that's because of the px. So next one, the tangential force is going to be coming over here, so that I am going to be writing ptx I am going to be considering, and it is going to be making an angle theta, right? This is the point C and this is going to be the F. Now I want to find out what is the pnx, what is the ptx. So that I am going to be writing pnx is equal to the px, so that's going to be adjacent component, this one, px cos theta, we will get it. Next one, ptx is equal to the px sin theta, we will get it. This is the opposite to this one we are going to be getting. So now we got the pnx and the ptx. So now what I am going to do, I want to take it for the FB face also. That is, this is the face is inclined to the FB. So then how could you write that part? So now we can see here, this is going to be your FC face, and here this is going to be the PY is going to be acting. So then in this case what will happen, this is going to be your FB face, and here this is going to be the theta, suppose. So then what happened, this force I am going to be resolving, one is going to be normally to this one, right, and the second one is going to be parallel to this part I am going to be considering. So that I am going to be taking over here in this direction. So here that I am going to be taking, this is going to be your P and Y is the normal forces, and here also making an angle theta, this is going to be the downward direction, that is the PTY I am going to be getting. So this is in the opposite direction. So then the P and Y is equal to PY sin theta, I got it, and PTY is equal to PY cos theta, we got it, because this PTY is going to be adjacent to this angle and this is going to be the opposite direction we are getting. So that's why P and Y, PTY, we got it. It means that this face is going to be subjected to the two type of forces. One is the in x direction, second one is the y direction. Now I will try to find out the resultant component for this part. So there we can see the total Pn is going to be acting, that is equal to, what is that one, Pnx plus Pny I am going to be considering, because the two forces are coming. Now I am going to be substituting these values, the Px cos theta plus Py sin theta, we got it, right? This value and this value I have incorporated. Then what is the Px? The Px already we defined in terms of the stress into area, that I am going to be writing sigma x is equal to Bc into this cos theta plus Py is going to be, I am going to be writing in terms of the stresses sigma y Fb sin theta, we got it. So once the Pn we got it, now I am going to be substituting in the normal stresses. What is the normal stress? The sigma n is equal to Pn by area, cross-sectional area I am going to be taking. That cross-sectional area is inclined to the BC, that is the FC face we have to be considered. So that I am going to be sigma x BC cos theta plus sigma y FB sin theta divided by FC into 1 we are going to be getting. And further simplification of this equation, if I am going to do, that's going to be sigma n is equal to sigma x. Then here I am going to be splitting the both sides, that's going to be BC by FC. Here is the cos theta plus sigma y FB by FC sin theta. Alright, now we know BC by FC is equal to, what is the value? So BC by FC is equal to, that means suppose you are going to be taking here, this is the BC and this is the FC. Can you see, this will become the adjacent component and FB will become the opposite component. So that I am going to be writing sigma n is equal to sigma x cos square theta plus sigma y sin square theta. So now I got the equation for this part. So now how should I simplify this equation? So as we know, the cos square theta is equal to, I am going to be writing here with the another terminology by using the trigonometry. So that I am going to be writing the sigma n is equal to sigma x into 1 plus cos 2 theta by 2, I can write it, right? Cos 2 theta by 2 I can write it. Similarly, sigma y is equal to 1 plus sine 2 theta divided by 2, I can take it, right? So this way I am going to be simplifying this equation. Sorry, over here, this is going to be the component of your sigma y is equal to 1 minus cos 2 theta by 2 we are going to be getting by the trigonometry. So now, can you simplify this equation here? So that's going to be sigma x, sigma y is there. So sigma n, that I am going to be taking here 1 by 2 over here. That's going to be sigma x plus sigma x cos 2 theta by 2, sigma y minus sigma y cos 2 theta, right? That I am going to be writing here. Further simplification of this equation, sigma n is equal to sigma x plus sigma y by 2, right? Plus sigma x minus sigma y by 2 into cos 2 theta. This is the way we are going to be calculating your normal force is going to be acting on your face FC. This is going to be your normal force shear stresses, that is the sigma n. Now we need to find out the tangential component tau we need to be calculate. Similarly, we are going to be taking the tau components. So now we are going to be taking the resultant component of the PT is equal to PTX, right? That minus PTY we are going to be taking because they are moving in the opposite direction. That depends on the x and y axis. So what is the PTX I am going to be writing? That's going to be sigma x BC, right? So that component I am going to be writing over here. Okay, that's going to be sigma x BC that I am going to be writing here is going to be, that's going to be sine theta minus sigma y FB cos theta we are going to be writing. So once we are going to be writing this one, the PT values, so now I am going to be taking the sigma t, that's going to be your PT. Now I will write the sigma t. This is going to be sigma t, or I am going to be taking the tau. The tau is nothing but the shear stress acting on your face FC. So that is equal to the load by area, that's going to be PT by area, I can take it. So that area is equal to be FC into 1 we are going to sigma x BC sin theta minus sigma y FB cos theta divided by FC into 1 we are going to be taking. So further simplification of this equation, what I am going to be writing, that's the tau is equal to similarly sigma x BC by FC, that is the sin theta minus sigma y FB by FC cos theta. Now we know what is the BC by FC. So BC is nothing but your adjacent component, right? BC by FC is going to be, again I am going to be writing here is the tau is equal to sigma x cos theta sin theta minus sigma y FB by, that's going to be sin theta cos theta. So in this case, and I am going to do the further simplifications of this equation. So what we are going to be writing? So in this case, cos theta is going to be the common here. So that I am writing the tau is equal to sigma x minus sigma y. That's going to be cos theta and sin 2 theta. Sorry, sin theta. So if I am going to be simplify this trigonometric equation, what I am getting, the tau is equal to sigma x minus sigma y, right? That's going to be sin 2 theta we will get it divided by 2. Right, that is going to be your trigonometry. Sin 2 theta is equal to the 2 into sin theta cos theta we will get it. So then further simplification, the tau is equal to sigma x minus sigma y by 2 sin, we are getting sin 2 theta. So can you see, this is going to be your the final derivation. It means that your FC force, this is going to be your FC, and one is going to be your normal component with the sigma n, another is going to be your tau component. That means that inclined plane or oblique plane is going to be carrying the two types of stresses, sigma n and the tau. So then FC is not going to be your principal plane. The principal plane is nothing but which plane have a zero shear stresses, then only we can say that part. So now we can see where we are going to be getting the maximum values. Then how to find out the obliquity. So in this case, we have derived the resultant component of the sigma x as well as sigma y. And again, this face is going to be subjected to the two forces. One is the normal as well as the shear. So then I'm going to be taking the resultant component r is equal to, that is going to be the square root of sigma n square plus sigma tau square. Whatever the magnitudes we are getting, then we need to be substitute. So this way we are going to be calculating the components. So next one, how to define the obliquity over here. So here I am going to be read out that part. So that's going to be angle made by the resultant stress with the normal of the oblique plane is known as the obliquity. So that we are going to be calculating, that's the obliquity plane angle tan pi is equal to. What is the formula we are getting here? The tan pi is equal to sigma, that means shear stress by normal. So this is the way we are going to be calculating the normal. That means it is not moving in this direction. So that means the resultant component can move. This is going to be a resultant component. Alright. So this way we are going to be, once we are getting these values, the shear stress as well as the normal stress, we are trying to make it here. So what is the maximum principal plane? What is the maximum shear stress we are going to be calculating? So as we discussed here, that is going to be the shear stress is carried on your facing. Then when it will going to be the maximum shear stress. So when this component will going to be the 1. So that's going to be sine 2 theta is equal to 1. So then when sine theta is equal to be 1, when 2 theta is equal to here, the 90 degrees or 270 degrees. So then the theta is equal to at 45 degrees and 135 degrees. We are going to be getting the maximum shear stress. This is going to be developing, right? So now we need to find out the maximum normal stress. When it is going to be the maximum normal stress we are going to be getting, that's going to be when cos 2 theta is equal to 1. So on that basis we derive the equation. So we need to find out the location of the principal plane. When the principal planes are going to be locating, when the shear stresses are going to be equal to 0. This magnitude I am going to be equating to 0, so that I will get it that components of the maximum shear stress on the planes here. So that when I am going to be taking here, that's going to be sigma x minus sigma y by 2 sine 2 theta, suppose. So then in this case what will happen? So that is going to be your sine 2 theta is equal to 0, suppose. This is going to be sine 2 theta is equal to 0, and this component will never going to be equal to 0, but sine 2 theta will going to be equal to 0. So then the theta is equal to either 90 degrees or we are going to be getting here. So that's going to be 0 or 180 degrees or 90 degrees. That means here 0 degrees or 180 degrees we will get it. That's going to be 2 theta. So once you are going to be getting, simply the theta is equal to 0 comma 90 degrees. If I am going to be substituting in this equation, what I am going to be getting? Here when theta is equal to 0, so then what will happen here? This equation, the sigma n, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 into cos 2 theta. That's going to be here the cos into 0 we are getting. So cos 0 means 1 we are going to be getting over here. So sigma n is equal to, I am writing sigma x by 2 sigma y by 2 plus sigma x by 2 minus sigma y by 2. So this will going to be cancelled. Then sigma n is equal to sigma x we are going to be getting. So when the theta is equal to 0, then we are getting the maximum normal stresses are equal to the direction which is perpendicular to that, in the same direction we are getting. That is normally directions is equal to on FC phase, that will becomes the BC. So now if I am going to be substituting the theta is equal to 90 degrees, so then what happened? So now this case I have taken theta is equal to 90 degrees. Then I am going to be substituting in that equation. So then finally sigma x plus y by 2 plus sigma x minus by 2 into cos 180. The cos 180 means we are getting, that's going to be 180 means cos. So the finally this value will become minus 1. So if I am going to be substituting in this equation, sigma n is equal to sigma x by 2 plus sigma y by 2. This will going to be the minus sigma x by 2 plus sigma y by 2. So this will going to be cancelled. Sigma n is equal to sigma y. So can you see, when the theta is equal to 90 degrees, and then sigma n, that is going to be the normal stress acting on your face FC is going to be equal to your FC. That's going to be FC will going to become FB. If theta is equal to 0, then what happened here? So that's going to be sigma n is equal to be sigma x. That FC will become the BC. This way we are going to be calculating your maximum principal stresses we are going to be calculating. That means normal stresses as well as the shear stresses we have calculated, which are inclined to the applied forces. As we know, when the faces are going to be subjected to the normal forces, so then that face only that stresses are there is no shear stress. But when the face is going to be little inclined, so this is the face and this is the inclined face, surely this face is going to be subjected to the two types of normal as well as the tangential. So thank you. Still, if you feel any difficulty or any confusions, please put in the comment section so that I can reach you out. Thank you.